Hello, everyone. I'm Valeria Nico from the University of Limerick. And today I'm going to show you in more details than the poster how vibrational energy harvesting can be used to power industrial IoT sensors. So if we consider a temperature sensor, this is made up of 4 building blocks, as I show you in the poster. So we have a powering system that is made up generally by batteries or physically wired power supply. We have the electronics, so a conditioning circuit and a microcontroller. We have the sensor itself. So in the case of a temperature sensor, it can be a thermocouple. And then we have a transceiver that will communicate using communication protocols to our gateway. So it is estimated that there will be 34.2 billion devices connected to the internet by 2025. Probably this number will increase considering Japan planning to deploy a lot of billions of RFID sensors. So one of the main issues with all these devices is that they are battery powered and the battery needs to be replaced before their expected lifespan. And in very large wireless sensor networks, battery replacement is not feasible because if we consider a large factory, your facility manager could end up changing even 30 batteries each day. And this will become basically a full-time job, just going around and changing batteries. Also, batteries, if not properly discarded and recycled, represent a significant environmental hazard because at the moment, just in Ireland, only 47% of the battery placed on the market are actually collected for recycling. Also, the materials that build the batteries are mined and large quantities of metals generally are released into the environment, representing pollution for our soil and water. And we have also to consider that generally rechargeable batteries, if you think of your Fitbit, are sealed into the device. So if your battery fails, you have to dispose the whole battery. So again, the whole battery replacement has a strong environmental impact. So what I'm trying to do is to take the powering system and replace it with energy taken from the ambient. That can be solar energy, wind energy, thermal, and the vibration. And in particular, with energy harvesting, we are focusing on the powering system and the electronics that is necessary so that at the end, you have your nice and steady 3.3 volt voltage. So if we look at the different types of energy that's available, I decided to focus on vibration for my research area because they have high enough efficiency, high enough power densities, but also they are very common in many applications. So we can apply vibrational energy harvesting to different applications such as wearable devices, transportation, mining, and Industry 4.0. So if we go into a bit of more details of how a vibrational energy harvester is made up, this is based on a very simple system that probably all of you is familiar from a bit of dynamics. So an energy harvester is based on a mass spring damper system, and we have an element called transducer that will enable the conversion. There are 4 generally types of conversion methods. One is relying on piezoelectric materials. One is relying on variable capacitors. We can rely on magnetostrictive materials. And finally, we have electromagnetic induction. So again, in my research area, I'm focusing mainly at the moment on electromagnetic induction because it gives you one of the highest power density at kind of centimeter scale. So converting energy from vibration, it's not easy. It comes with big challenges because if we look at the frequency content of the different ambient vibrations, so the frequency content would be like the fingerprint of your ambient vibration. These are very different. So the plot on the left shows you the frequency content of an ideal harmonic vibration, so it's single frequency. But then on the other two plots, you have the frequency content of the acceleration of an industrial air compressor and the acceleration of a mining screening machine. So you can see the frequency content is very different. So ideally, our device might need to have an easy tuning feature so that I can use the same device, adjust it a bit, and use it in different scenarios. Also, we have the ambient vibration have multiple peaks. So ideally, I would like not just to have a device that works only at one frequency. I would like something that works at more frequencies. So I would love a multimodal harvester. And at the moment, commercially available harvester can harvest only energy from one frequencies, and they don't have any tuning mechanism. So if you buy a device that works, I don't know, at 50 Hertz, you can't modify it to work at 60 Hertz. You have to buy a completely new device. So in Stokes, that is my group in UL, we developed a multimodal harvester that is made up of two masses, and we have coils and magnets moving inside the other. But the particular thing is that we added a tuning feature. So we have actually, we can change the internal size of the harvester, and this will change the frequency response of the device. So one of the main questions that I'm always asked is actually how much power I can get from such device. And unfortunately, there's not an easy reply, because the output power depends on the vibration source. So it depends on the frequency content of the vibration source, but also on the amplitude. Generally, they are vibrational energy harvesters are characterized using harmonic excitation, so a single sinusoidal acceleration. And this will give you the maximum output you can ever get. Unfortunately, real vibration are a bit more noisy with multiple frequencies and modes that lower down the power available. So if we consider first the output power in the ideal case, this is the maximum power ever that you will ever get from the device. And I'm considering two different acceleration amplitude. In both cases, you can see that there are two peaks visible, and this is the multimodal feature of our harvester. And also going from the blue line to the purple line, we are adjusting the internal size of the device. So you can see that we are actually, you can shift the second peak towards the right. So you can actually adjust the frequency response of the harvester. And this is the tunability feature of the harvester. And finally, as I mentioned, you can see easily that the output power depends significantly on the acceleration level. Since at the higher acceleration of 0.6 G, we get higher output power compared to the other case. We also developed our power management circuit that features AC/DC conversion and MPPT to maximize the output power that is stored on a supercapacitor. And we decided to choose a standard 3.3 volt output because it's currently what most of commercially sensor boards use. So this makes this whole system suitable for different IoT communication protocols. We decided to test our system with two different sensor nodes. One is the LoRaWAN sensor node developed by Pervasive Nation, and the other is a commercial Bluetooth device. And also we considered two different compressors. So the two compressors have, they're still an air compressor, but you can see that they have different amplitude and different frequency content. And that's why it's very important to know exactly where your vibrational energy harvester will be placed to tune it to the ambient vibration. In the first case, we were able to harvest 0.29 milliwatts of power on the capacitor. So this is what it's actually available. And we were able to achieve a transmission time of 30 seconds with the LoRaWAN board and transmission times of 2 seconds with the Bluetooth board. And this is faster than what you can achieve with a lithium battery if you want a 1-year lifetime. Because in that case, your battery has to transmit every 5 minutes. In the second case, we considered the second compressor. So the harvester in this case was mounted on the motor of the compressor, and we monitored the charging of the supercapacitor over time, and that's the plot you can see at the bottom of the slide. And we were able to harvest 9.4 microwatts of usable power that translate into transmission times of 15 minutes for the LoRaWAN sensor. So you can see that there's significant difference in harvested power that translates into transmission times. But again, you can, with vibrational energy harvesting, also in this case, you can achieve transmission rates that are suitable for industrial monitoring application. So to conclude, I hope I kind of give you an overview of the capabilities that vibrational energy harvesting has as a substitute to batteries. And we decided to develop a multimodal harvester with its own power management circuit that was able to energize a LoRaWAN board every 30 seconds using the first compressor, and the time increased to 15 minutes with the lower vibration of the second compressor. In both cases, times are suitable for industrial monitor application. Thank you very much.